second order differential equations is going to be one of the main focus here. But in the beginning here, 4.1, we need to develop some theories and some approaches to being able to solve for this. So it is important to remember that we're still going to be stuck with the linear differential equations. If it becomes not linear now, it becomes a little bit more difficult to solve. So in this chapter, we're going to focus on linear differential equations. And if you remember what a linear differential equation is, you can have any sort of floating functions as coefficients to y or any derivative of y, but as long as y or its derivatives are not being raised to a power, are not being put into a function, then you're all okay. So you can have these coefficients as functions of x, as complicated as you want them to be, but the y's themselves are not being raised to any power. So that's your differential equation. Now, because you have a higher order differential equation, your initial conditions will also have to change. And what's going to happen is that this should be x, not. What's going to happen is that you're going to have as many initial conditions as the order of your differential equation. So an IVP for first order differential equation looks like differential equation dy dx plus px times y is equal to q of x. That's a first order linear differential equation. And then your initial condition is x naught, y naught, and you only have one initial condition for that. When you start going to higher orders, you're going to have to build your initial conditions as well. And the initial conditions are going to be based on the original function and one less as many derivatives as the order. So, for example, if your differential equation looks like this, looks like y double prime plus 4y is equal to 0, then your initial conditions might look something like this. Y of 0 is equal to, I don't know, 0, and then y prime of 0 is equal to 1. So this is a second order differential equation, and if this was going to be an initial value problem, I would need two initial conditions to satisfy my initial value. Okay. So that's your IVP for a higher order differential equation. All right. Going beyond this, there's a special theorem in differential equations called the existence and uniqueness. We saw that with the first order, and so here we can see the existence and uniqueness for higher order differential equations as well. And that would look like this. And the existence and uniqueness theorem really just gives you conditions for your IVP. so that you can actually have a solution. All right, so here's the key. You got those coefficient functions are all continuous, and the function on the other side of the equal sign is also continuous. And here's one of the important aspects of finding an interval, the largest interval, where your solution will exist, would be in an interval where the leading coefficient function is not equal to 0. So wherever those things are equal to 0 would be the breakpoints of your solution. So x is equal to x naught is any point in the interval, then the solution y of x exists and is unique. So there can only be one solution once you find that solution. And it exists, so whether you can find it analytically or not, it's a different story, but we know that there's something that exists there. We can at least draw the solution or something. Okay? So let's see if we can, I don't know what the example problems are here. Find a member of the family as solution and initial condition. We know how to do that. Let's see. Here, find an interval centered about x is equal to x naught or x is equal to 0 for which a given initial value problem has a unique solution. So this one is one that would use the existence and uniqueness theorem. So let's take a look at this problem. So this is a second order differential equation. We have a few functions involved here, our coefficient functions, namely this x minus x naught, or this x minus 2, I mean, is your leading coefficient. So we can think about that as looking as a2 of x. If we cared about it, which we won't, a1 of x is equal to 3. No, sorry. I made a mistake. What's a1 of x equal to? So our n is equal to 2 in this case, second order. I have y double prime, the coefficient of that is a2. What's a1? No, I thought it was 3, but it's not. What? 0. So a1 of x is 0, which is a valid continuous function on any interval. And this is a 0. And then this last one is what they refer to as g. And there's 0 times y prime here, which is why a1 is 0. So again, none of these other ones are as important as this first one. So this first one is when that's equal to 0 is what we should be concerned about. So x minus 2 equal to 0 when x is equal to 2. So we have an issue at 2. Our differential equation is probably not going to be continuous there. Now, whether it's a vertical asymptote or something else, we don't know, or we don't know right now. I think we'll eventually find out. But at this point, this is all we know. So we're looking for an interval around 0, so the initial conditions here say that we're about 0. And what happens is that to find your interval, to find the interval that we're looking for, we have an issue over here when x is equal to 2. And so you'll see that when we study this a little bit further, we're also going to go as far as 2 on the negative side. So if it's centered around 0, then our solutions will only go as far as the first time we see a discontinuity on, or not a discontinuity, but a 0 on the first function. So our interval in this case is from -2 to 2. Does this look familiar? Does this remind you of anything that you might have done before? Convergence. What's that word before convergence? Radius of convergence. So this all kind of comes from the idea of a radius of convergence. So in one dimension, which is what we're dealing with here, just the t-axis or x-axis, in one dimension, our circles are just intervals. Now, we're not going to study this in the complex plane, but technically you can put complex numbers here, in which case your complex numbers can be described in 2 dimensions. Oh, maybe we will look at complex numbers after all. In any case, complex numbers start dealing with things that are 2-dimensional, and so the radius of convergence makes a little bit more sense there, because you're looking at circles around center points. And then so you got the distance being the radius. But for now, if you want, think about it as a circle, and then you have the radius of convergence there.
So if x is 2 or larger, does that mean that right there doesn't exist?
The solution. The solution won't exist. Well, here in this case, the initial value problem has us stuck here when x is equal to 0, and then we have a break here at 2, and so we can't go beyond 2. The chances are when we do this stuff, we're going to divide by x minus 2, and so when you divide by x minus 2, you can't have x equal to 2, because you'll get some bad stuff. Okay? All right, so that's a little bit about the existence and uniqueness theorem. So we know that we can find a solution. I mean, we can find a solution. We don't know if we can find it explicitly, or we don't know if we can find it symbolically, but there is a way to find a solution here. And we'll take a look at the techniques that they're going to talk about in this chapter. All right, existence and uniqueness. Next is boundary value problems. So instead of IVP, initial value problems, they have what they call boundary value problems. And we're not going to talk too much about this. We're not going to dwell on this too much, but I think it's worth mentioning that sometimes, instead of giving you an initial condition from one point, they give you what's called a boundary condition from 2 points. And this works best with second order. I don't know how well it works with like third or an odd order, but if you have a second order differential equation, to your differential equation, instead of giving you an initial condition, and an initial condition would look something like this. It would look y of 0 is equal to 0, and y prime of 0 is equal to 1, or something like that. Instead of giving you an initial condition comes from one single point. Instead of that, they give you two different values of either the y or the y prime or a combination of that. It gives you two different values of how this thing would look like. So that's how a boundary condition might look like. But the boundary condition doesn't adhere with the existence and uniqueness theorem. The existence and uniqueness theorem only applies to initial value problems. So if you have a boundary value problem, you could conceivably have more than one solution, which makes it not unique, or you could possibly have no solution, which makes it not exist. So it could break the existence and uniqueness theorem if it's not an IVP. So a BVP, boundary valued problem, does not guarantee the existence and uniqueness of your solution. All right? So like I said, we're not going to talk too much about this. We're going to focus on initial value problems for these higher order differential equations. What's next? All right, so that's the main part of the theory. Now let's actually dive into trying to solve for these differential equations. And I know we defined the word homogeneous came from something already. Oops, I don't know what that is. But here's the here's a term that I'd rather have us remember for homogeneous equations. So I guess what I'm trying to say is the homogeneous equations that we talked about last time, just scratch that from your memory for now. And from now on, when we think about homogeneous equations, let's think about something that's set equal to 0. So a homogeneous differential equation is a differential equation where if you write it in standard form like this, there's a 0 on the other side. So that actually will make our work a little bit easier. So it also turns out that if you're solving for a non-homogeneous equation, the first step to your solution is to solve the homogeneous equation first. It's kind of a neat idea. So the homogeneous differential equation is our easier path or easier differential equation that we're going to solve. And once we're comfortable with that, we're going to move on to non-homogeneous, which also looks for you to solve for the homogeneous part. Okay? It's always hard to start a new section of something because you've got to lay out all these theory first before we actually do an example. We haven't really done an example where we're actually solving for the differential equation. We're going to have to wait a little bit longer to solve for one of these differential equations. So, homogeneous differential equation. Just to pile on a little bit more theory, there's this idea of what's called a differential operator. A differential operator is D. So when you think of saying D of something, think of it as just a derivative. So usually we say d dx, right? But to have a capital D just kind of frees us a little bit of our independent variable. And we can also extend the idea to having it be the second derivative, a third derivative, without doing the d dx squared, d dx to the third power, and all that complicated stuff. So if we just call capital D as your differential operator, then it's easier to use as a notation. So it turns out that if we have a linear differential equation, we're able to use the capital D as a differential operator that would take derivatives of things. And then we can make it even look fancier or whatever by just denoting whenever we have a second derivative, we'll call that D squared. Whenever we have the first derivative, we'll call that D. And whenever we're looking at the original function, think about it as the zeroth derivative, we'll just call it a 1, or D to the 0. So think about y as d to the 0 of y. Think about y prime as d to the first power of y. Think about y double prime as d squared of y. And then with this notation, it turns out to be a nice convenient notation for us, because we could just call this whole thing your linear operator. This is your derivative operator. Okay? So just as another example, dy dx plus 3y is equal to 2x, or something like that. You can write this in a D notation as dy plus 3y. Is equal to 2x. I think I'm joking. So the differential equation can be expressed this way, where you have the D operator involved here. So what does that mean for us? In terms of solving for these things, it doesn't really mean much. Again, this builds up on a theory to help us find solutions of things. But there is one important aspect of these differential operators that's important, and that is that these differential operators are linear. Now, linear is an idea that's discussed in great detail in linear algebra. How many people have had linear algebra? So a linear operator is an operator that satisfies this condition. And there are two linear operators that you guys know well, whether you know that they're linear or not. What are they? What? What are the two linear operators that you guys should know really well? What? Linear operator? So two examples of linear operator is the derivative and the integral. Taking the derivative is a linear operation. Taking the integral is a linear operation. And for it to be a linear operation, it has to satisfy this condition. What does that mean? What does this L, alpha, beta, F, G, that business, that looks complicated. Well, if you break it down to something that you guys are already familiar with, d dx of 2x squared minus 5x without actually doing this, because you guys do derivatives really quickly now, but without actually doing the derivative and just look at linearity, what you're really doing when you first learn derivatives is that you're breaking this up into two different terms. So that's the part where you break up this sum into two different terms. And then you're going to take the constants out. And then you would take the derivative. Okay? So that makes it linear. Integral is the same thing. And by splitting your integral up like the way you're used to splitting it up and taking the constant out, you're essentially saying that I'm using these properties because the integration is a linear operation. All right. So it turns out that this operator, if I look at d plus 3, that's also considered as a linear operator. If I look at d squared plus 5d plus 6, that's also a linear operator. So these are all linear operators, which means we can take advantage of splitting them up term by term and then taking the constants out. Okay? So that's still not the best thing about the linear operator, or the fact that we're dealing with linear operator. The best thing about it is that we can use this next theorem, which is the superposition principle. And this will get us going with our, well, it still doesn't get us our solving for the differential equations, but it'll dig us into more theory behind our solutions. So this is kind of cool. If we have an nth order differential equation, homogeneous differential equation, so let's start off with homogeneous, having that set equal to 0. If y1 is a solution to the differential equation, and y2 is a solution to the differential equation, then if you multiply that by a constant and then add it to y2 multiplied by a constant, then that's also going to be a solution to our differential equation. That's really interesting. Because what we want to do is we know that if this is an IVP, that we're going to get a unique solution, and so we want to make sure we gather all the possible solutions that we have and put it all together as our general solution. Let's take a look at an example. I have a homogeneous differential equation over here, and I'll say that y1 is equal to, let's say, sine 2x is a solution. Let's check that. Actually, I want to put it here. So let's check if this is a solution. We need a couple of derivatives. And then let's put it back to the original equation. We have minus 4 sine 2x plus 4. This is y double prime. Plus 4, and then y is sine 2x. And that is, in fact, equal to 0. Right? Now, what if I also said that I have another solution for this? I think another solution to this is cosine 2x. Let's check if that is, in fact, a solution. I need a couple of derivatives again. So the first derivative, the second derivative, and then put that into the original differential equation. I need y double prime plus 4 times y. And that is also equal to 0. So yes, this also works. Right? So according to this superposition principle, if I have two solutions to my second order differential equation, that means this, where I have y1 times a constant plus y2 times another constant, doesn't have to be the same, it could be a different constant, and I add them up as two different terms, then this must also be a solution. And I'm not going to do it because it was on your test and most of you got it right. So you take the two derivatives of it and then put it back into the differential equation. You'll see that it actually works. Okay? So it turned out that the first solution worked, the second solution worked, and so this is a general solution that should also work. Yeah, you add them both together with constants as coefficients, and then they would also become solutions. That's according to the superposition principle here. You got solutions, and then the linear combination, and when you hear a linear combination, it's a constant times 1 plus a constant times an x plus a constant times an x. So a linear combination of them is also going to be a solution to the differential equation. And in fact, this is the most general this is your general solution to your differential equation. Okay? Now, if you had initial values, you would use the initial values to solve for C1 and C2. Again, something that you guys did in your in your exam, and most of you did well on that. So we'll talk about finding these values later on in more detail. So in terms of we don't have a specific initial condition here, but if we had an initial condition, your solution would look something like this, which means you can't have any other combinations because of the existence and uniqueness theorem. You can't have any other combinations that would give you your solution. So if you try any other function like e to the x, e to the 2x maybe, that looks like it might work for this, you'll see that if you try that, it won't work. But this is your general solution. Okay, so how I got sine x and cosine, how I got sine 2x and cosine 2x, we'll figure that out maybe today. But for now, I just kind of pulled it out of the air. A few other they call it a corollary. You know what corollary is? Okay, theorems are these big ideas, fundamental theorem of calculus. It's like a big idea where you suppose something is true, then this thing has to be true. Smaller theorems, in general, are called lemmas, L-E-M-M-A. So those are things that you would prove to help you prove your big theorem. And after you've proven your big theorem, there's things that automatically follow. Because the theorem's true, then all these other statements are going to be true. And that is called a corollary. So they're calling it a corollary. So these things follow directly from the result of the theorem. And the result of the theorem says if y1 is a solution, then a constant times y1 must also be a solution. And I can choose any constant I want. And also, if C1 and C2 are both equal to 0, then that's also a solution. So C1 and C2 equal to 0 means the whole thing is equal to 0, and that's going to be a solution to your homogeneous differential equation. And that makes sense because the right-hand side of your differential equation is 0. So if you wipe everything out of the left-hand side with all the y's, if y is equal to 0, y prime is equal to 0, y double prime is equal to 0, y triple prime is equal to 0, then everything on the left-hand side will be 0. That's going to equal to 0 from your homogeneous differential equation. So if we look at this example here, you have your differential equation, your homogeneous differential equation, and you have your y1 and your y2. This is a second order, so we should expect two solutions. then that means y is equal to 14x cubed is also a solution. Y is equal to 3x to the fourth is a solution. Y is equal to 7x cubed minus 4x to the fourth is also a solution. So any linear combination, including when one of the C1s or C2s equal to 0, or both are equal to 0, those are all solutions. So the idea is that if I take any of these and put it back into this differential equation, I should get a true statement, right? Should we do one? Or are you guys convinced? You guys are boredly convinced, huh? All right, we'll get to solving for these things soon enough. So that's what the corollaries say. All right, more boring, more linear algebra stuff. If you've taken a completed linear algebra, you should be sick of the word or the phrase linearly independent. So a set of functions, these are functions with x's now, are said to be linearly independent or linearly dependent if I can find constants that are not all equal to 0 so that this thing will end up being equal to 0. What's that mean? Let's take a look at an example. Let's see. Let's let f of x, well, I'm going to use y. y1 is equal to x squared. y2 is equal to x. And y3 is equal to 2x squared minus 3x. Now, these three functions are linearly dependent if I could take those functions and then multiply each of them by something and then add them up and force this to equal to 0. Now, can you find any numbers that I can put in these blank green spaces that would make this thing equal to 0? What? Except zeros, not all zeros. Let me underline that. Not all zeros. 2, -3, and 1. So if I can find these numbers like 2, -3, and 1, so that if I multiply each of those by the first one by 2, and the second one by -3, and the third one by 1, and if you distribute, lift parentheses, and simplify this, this would in fact equal to 0. Right? Oh, -1? Yeah, -2, 3. So it doesn't matter what, as long as you can find one set of numbers that are not all zeros that would make this disappear, that would make this go to 0. Then we have to say, we can conclude that this is linearly dependent. Okay? Now, if I had y1 is equal to e to the x, y2 is equal to e to the 2x. If I can ask the same question, can I find a couple of numbers to multiply? I can only put numbers here. I can only put scalars. So either numbers, real numbers, or complex numbers. But can I find a number or two numbers here that's not both equal to 0 that would make this equal to 0? And the answer is no. So I can't find numbers to make it all equal to 0. So that means this thing must be linearly independent. Now, checking it this way is not the most efficient way, right? You kind of have to be guessing. You guess, what if I put 0 and 1? No, that's not going to work. What if I put 1 and -1? No, that's not going to work. What if I put 5 and 3? No, it's not going to work. So that, doing this is not the most efficient way of doing things. So what we're going to do is we're going to see if we can find another way to find linear independence, because it is important to know when two things are linearly independent or not. Because if they're linearly dependent, then when we're counting the number of functions that we have to build up our using a superposition principle, here we have two functions, x to the third and x to the fourth, that satisfy this equation. The question is, are there any more? Well, wait. Before that question, the question is, are these two linearly independent or are they dependent? And we'll see that they're actually independent. You could try to see. So now that we know that if they are in fact independent, then we know that we have two solutions, and this is a second order differential equation, so that should be all our solutions. We can't have any more solutions. But your solutions have to be linearly independent. So that's why we're taking a look at what it means to be linearly independent. Okay, because we need to count the number of solutions that we're getting, and then we need to match up the number of solutions with the order of the differential equation. All right, so a quicker way, hopefully a quicker way to find out if something is independent. So a quicker way to figure out if something is linearly independent is what's called the Wronskian. Wronskian. You should say it out loud once in a while. Just walking down the street and just say Wronskian. So the Wronskian is the determinant of a matrix of functions that you're trying to show whether it's independent or dependent, linearly independent or dependent. So they start off with the definition. This is a definition of the Wronskian. You have n functions, and they all have n minus 1 derivatives. And the Wronskian is going to be the determinant of this function. And the theorem, the following theorem here, is going to be our magic bullet to figure out if something is linearly independent. If you have a set of functions that are solutions to the homogeneous differential equation, a set of functions are linearly independent if and only if the Wronskian is not equal to 0. So if the Wronskian turns out to be equal to 0, then the set of functions that you put in there are linearly dependent. If it's not equal to 0, then the functions you put in there are linearly independent. Okay? So let's use the two examples that we did, except one of them had 3. Yeah. Oh, let's see how that'll work out. What was it? 2x minus 3, 2x squared minus 3x. All right, let's find the Wronskian of this. And we said that this was dependent, right? So the Wronskian should equal to 0. So let's see if that's true. Now let's see how the Wronskian is laid out, too. So the Wronskian means I want to make a matrix out of this, and then I'm going to take the determinant. So the first function is x squared. Doesn't matter which one's first, I guess. We could switch things around. The second function is x. The third function is 2x squared minus 3x. Now, just down below, I just take derivatives. So I need this to be a square matrix. So I have 3 rows, or 3 columns, so I need 3 rows. I have the original function in the first row. I need the first and second derivatives. So the first derivative is 2x, 1, and 4x minus 3. The second derivative is 2, and this is 0, and this is 4. Do you know how to find the determinant of something? Damn. We have to talk about that, huh? To find the determinant of a 3 by 3 matrix, you put it into Wolfram alpha and get the answer. All right. To find the determinant of the matrix, to find the determinant of a 2 by 2 matrix, it's easy. You multiply the diagonals, and then you multiply the wings, and then you subtract them. And we'll do an example of that. Yeah?
How do you, is it just until the second column?
Yeah. So there's 3 functions here, and the Wronskian is looking for 3 minus 1, so just up to 2 derivatives. What? Yeah. I was going to use the last row, but we can use either one. So the idea is to expand on one row or one column. And then if you have any zeros in there, you should be happy, because that's, you want to expand on a row or in a column that has zeros. So I was thinking of expanding along this row, the last row, but Sadie said that maybe it might be easier if you expand on this column. So this is how we would do this expansion. So we're going to expand on this column. And what you need to do is that when you move around your matrix, you're going to start off with at the first row and first column as a positive. And whenever you move to one space up or down, it becomes a negative, and then positive and negative and positive. So all these have signs to it. Okay? So that's the first thing to remember, is that they have signs. The next thing is that my x, I want to expand on this second column, so I'm going to start off with this x. So the determinant is going to equal to, so it's x, but it's negative, right? So it's negative because of the place where I'm starting, and this is my value. Now what you need to do is you need to cross out whatever number you're working with. You need to cross out that particular row and that particular column. Okay, so I'm expanding on x first, so I'm going to cross out x, the row that x is in, the column that x is in, and the row that x is in. So I'm going to cross that out. And what do I have left? I'm going to have left the matrix 2x, 4x minus 3, 2, and 4. And then I'm going to take the determinant of that. Now I need to, I'm expanding on the column, so I need to go to the next one. The next one is 1 with a positive, so plus 1. And then now I need to expand after crossing out the second row and second column. And that would leave me with a submatrix x squared, 2x squared minus 3x, 2, and then 4. And then now I'm going to expand on my last one, which fortunately is 0. That means 0 times anything is going to be 0. So that's why you would want to choose a matrix that has, or choose a row or column that has a 0 in it. And I'm not going to bother writing that down, but if I was to write it down, it'll be x squared, and it'll be 2x squared minus 3, 2x, and then 4x minus 3. But it's all going to disappear, so I'm just going to put a star. Now, to find the matrix of the determinant of a 2 by 2, I just multiply the diagonals and subtract the wings. So 2x times 4. No, it's just 2x, because the pluses and minuses here only apply to that first one when you're expanding. And once you do that, then you're just focused on the actual values. Only one row or only one column. So I have 2x times 4, and then 2 times 4x minus 3. So that's the determinant of this first 2 by 2 matrix. Now I have 1 times, and now the determinant here is 4x squared minus 4. I was going to multiply everything out, but let me just say 2 times 2x squared minus 3x. All right? So if we multiply all this out, this becomes negative 8x squared positive 8x squared positive negative 6x plus 4x squared minus 4x squared plus 6x. And so it looks like it all disappears. Okay. So now to actually show that other one, the e to the x and e to the x squared, that one's a little easier. In fact, I think I could squeeze it all into here. As our other example. So if we have this, the Wronskian is going to be e to the x. What's the derivative of e to the x? E to the x. And then here, e to the 2x, the derivative of that, 2e to the 2x. So it's only a 2 by 2 matrix, which makes it nice and easy. Here we have 2 e to the x, e to the 2x. I suppose we can add the exponents there, right? Minus e to the x, e to the 2x. And that's, is that 3x, e to the 3x? So this is 2 minus 1 is just 1 e to the 3x, which is not equal to 0, or not exactly equal to 0, which means this is independent. Right? All we said in the previous page was, well, we couldn't find two numbers that would make that equal to 0, so that's independent. But now here we have a more surefire way of showing independence. Okay? All right. I think that's it for the boring part. I mean the theory part. Oh, one more. A couple more pieces of information. Fundamental solution set. So here's the key. Here's the rest of the theory that I've been kind of saying all along. If you have an nth order differential equation and you found n linearly independent solutions, then all those solutions are the fundamental solution set for your differential equation. All right? There's that existence theorem again, and then the last theorem here says that the general solution is equal to this. So back to our first problem, or that problem that came from the exam. We got y double prime plus 4y is equal to 0. And then we said y1 is equal to sine 2x. y2 is equal to cosine 2x. Turns out that they are linearly independent, and you can use the Wronskian to prove that. So sine 2x cosine 2x, that's the derivative. Second function, cosine 2x, a derivative, negative 2 sine 2x. So the determinant, sine squared minus cosine squared and they both have negative 2 in front, so you can factor out a negative 2. And then you have sine squared plus cosine squared, which is equal to 1. So we have a constant. More importantly, we have something that's not equal to 0, so we know that they're independent. Right? So the fundamental solution set would just be listing those functions, and then your general solution is going to be C1 times sine 2x plus C2 cosine 2x. Okay? All right. So next time, let's actually dig into this differential equation and see how we can actually find these solutions. Because right now I'm telling you these are the solutions and they exist, and then so we're finding out information about each of these solutions. But next time we'll actually dig in to see how we're finding these solutions. All right, that's it for today.